An interesting thing we could discuss is what exactly is curl in the physical world.
Shall we?
Yes, we shall discuss it. So, let F be a vector field. S sub A be a small circular disk of radius A centered at XYZ, that's somewhere in our vector field, and the boundary of some curve, some little tiny circle, let's say CA, running counterclockwise. Okay, we got a small circular disk centered at some point XYZ in a vector field, and the boundary is some curve, really a circle, going counterclockwise. At each point on the circle C sub A, the normal component of F is F dot n. Now you know why that is, right? And the tangential component of F is F dot T. You should know why that is too from the first unit, right? Knowing what the dot product is. So if F was aligned with T, then the value of F dot T would just be as large as possible, and hence a fluid will tend to move along a circle rather than across it. Therefore, the line integral of F dot T around the circle CA measures the circulation of the vector field F around the circle C sub A. So the circulation of F around the circle C sub A is the line integral of F dot T ds over the curve CA, and we got it in a picture here. The curl of F, well, here's our vector F. Here's the tangential component of F. Here's the normal component of F. When you dot, you should get those. And so this is just a blow up of this picture here. So suppose that the disk SA is part of a surface S and is centered at XYZ on the surface. On such a circular disk, the vector curl of F is almost constant and hardly varies from its value at XYZ. Hence, curl of F dot n is also nearly constant on that piece of surface S sub A, because all unit normal vectors there are about the same. So what Stokes' theorem gives us, that F dot T ds over the circle C sub A is equal to the curl of F dot n times ds over the surface S sub A. So that's approximately the curl of F dot n times this surface piece, and remember this piece of surface is just a circle, so curl of F dot n times pi times a squared. Think about what that part would be. Okay, so from the last line in this, we get the curl of F dot n is the line integral of F dot T ds over pi a squared. Or another way of putting it, curl of F dot n is approximately the circulation of F around the circle over the area of the disk S sub A, remember that was the pi a squared, which is approximately the rate of circulation. We can assume that under nice conditions the approximation improves for smaller disks. In fact, it's natural to assume that curl of F is equal to the limit as A approaches 0, remember A is the radius of the disk, 1 over pi a squared times the line integral over curve CA, which remember is the border, F dot T ds. And this amount is called the rotation of F about a normal vector, right? So the curl of F dot n is the rotation of F about n at the point XYZ. In other words, the curl says at any given point how much rotation there is at that point about a normal vector to the surface. So it's logical to assume a rotation is maximal whenever the curl of F and n point in the same direction, right? thus maximizing that dot product. The tendency for a fluid represented by a vector field F to rotate may vary from point to point on a surface S, and Stokes' theorem, that's this theorem right here, says that the sum of the measure of this rotation over the surface S, that's the right side of this integral, which is a surface integral, is the same as the tendency of the fluid to circulate around the boundary of the surface C, that's the left side. So in other words, the measure of the rotation over the surface S is the same as the tendency of the fluid to circulate around the boundary of the surface, actually of the curve on the surface C, which is a line integral.